Hello and welcome to today's topic, Alkanes reactions. The outline for today is to look at the combustion reactions of alkanes, and after that we will have a look at the substitution reactions of alkanes. The alkanes are a family of similar compounds, and we already got to know methane, ethane, propane and butane, for example. All these substances share similar chemical properties because they all belong to the alkanes, and that means that all of these substances also undergo similar chemical reactions. And that's quite useful in organic chemistry. All the alkane substances will undergo the same basic types of reactions, no matter if we do the reaction with methane or butane or any other substance. And one important thing that can be done with alkanes is they can be burnt. And that's why they are also used as fuels. The general word equation can be looked at here. Alkane plus oxygen reacts to carbon dioxide and water. Let's get into more detail. Combustion reactions can be subdivided into complete and incomplete combustion reactions, and the more easy one is the complete combustion reaction. We have an example of propane reacting with oxygen, as the general word equation told us, to form carbon dioxide and water. Now this equation has to be balanced because we work with chemical formula, and we can see that one molecule of propane requires 5 molecules of oxygen to form 3 molecules of carbon dioxide and 4 water molecules. The oxygen supply of a complete combustion reaction is comparatively high because one molecule of propane requires 5 times as much oxygen molecules. Still, it's also true that a complete combustion reaction releases the most heat energy, especially compared to incomplete combustion reactions. The incomplete combustion reactions I want to illustrate at the example of butane. Here in brackets we have the complete combustion reaction, and we can see that butane requires 13 oxygen molecules to be completely burned. And yes, in reality we can't assume that there's always enough oxygen supply to burn the fuel completely. And that's why also incomplete combustion reactions take place. One possible reaction could be this one, where butane reacts with 9 oxygen molecules to form carbon monoxide, so CO, and water. Now, CO, carbon monoxide, is toxic and a very dangerous gas, but it can be evolved if the oxygen supply is too low to burn the fuel completely. Another reaction that is likely to take place is butane reacting with 5 oxygen molecules to form basically carbon, and we call this soot in that in this case. And because heat energy is released during the combustion of butane, the soot will start to glow and produce the orange color of the flame of a lighter, for example. We can conclude that an incomplete combustion reaction requires less oxygen supply compared to the complete combustion reaction. Yes, so we see the incomplete combustion reactions, they show smaller factors, 5 and 9, compared to the 13 here in this reaction. But at the same time, incomplete combustion reactions also release less heat energy compared to the complete combustion reactions. And a second type of chemical reaction that alkanes do is the substitution reaction. Substitution in general means that one atom is replaced by another atom. And in specific, it means that one hydrogen atom of an alkane is replaced by one halogen atom, namely chlorine or bromine. And you can see a displayed formula equation below. We have a methane molecule reacting with a chlorine molecule, and this hydrogen atom gets substituted, so replaced by one of the chlorine atoms of the chlorine molecule. And then we end up having this chlorinated methane as a product. It is a halogenated alkane, and we give it a name, the general name, halogenoalkane. So a halogenoalkane is formed, and as a byproduct, so to say, we have a molecule of hydrogen chloride. The product, so the halogenoalkane, is named like a branched alkane. So in this case, we would give it the name 1-chloromethane. And the 1 is obsolete in this scenario because we only have one carbon atom. So the table below tells you that if you have chlorine as a substituent, the name of the substituent is chloro. If you use a bromine, the name would be bromo. So far, so good. What we will do next is we will look at the mechanism of a substitution reaction, because this equation does not provide sufficient information about how a substitution reaction takes place. Because theoretically it could be that both chlorine atoms will substitute hydrogen atoms from the methane molecule to end up with a product like this. So then both chlorine atoms each substitute one hydrogen atom of the former methane molecule, and then as a byproduct we would obtain a hydrogen molecule, H2. This is not observed when carrying out the experiment. That's why we conclude that this reaction here on the left must be true, but theoretically this stuff here on the right could also be a substitution reaction. And we need more details about the procedure of the substitution reaction in order to really understand what happens, and that's what the mechanism of a reaction tells us. That's why in the end of this video we will look at the mechanism of substitution reactions. And this mechanism is subdivided into 3 steps. We have an initiation step, a propagation step, and a termination step. And the reaction is initiated by UV light. And UV light is quite energetic and is able to break the weakest bond in the system. And in a system where we have only methane and chlorine as reactants, we only have CH bonds and Cl-Cl bonds. And we can see that the Cl-Cl bond is much weaker, has a lower bond energy compared to the CH bond, and that's why the bond within the chlorine molecules breaks. This is due to the UV light, and the chlorine molecule splits into 2 chlorine radicals. So we call this species on the right side a radical because there is an unpaired electron. Basically, this is a chlorine atom, and this chlorine atom, respectively chlorine radical, is very reactive because it fails the noble gas configuration. It does not have 8 outer shell electrons, but only 7. So in the propagation step, this very reactive chlorine radical attacks a methane molecule, and it abstracts a hydrogen atom. And as the chlorine radical and the hydrogen atom bond together to form a hydrogen chloride molecule, which is very stable, we are left with a new radical, this CH3 radical, that is just the leftover of the former methane molecule. Now, this new radical can react with a chlorine molecule where the bond is very easy to break. We know this already. So bond is broken here, and the radical reacts with a chlorine atom or chlorine radical to form one molecule of the product, so this chloromethane. And then we are left with a chlorine radical. Now this chlorine radical can be reused in the propagation step, look right here, to react with another methane molecule. So what we have over here is a chain reaction. These two reaction steps within the propagation happen multiple times. And so hydrogen chloride and chloromethane are being formed. In the end, we also need a termination step. This means the reaction somehow must come to an end, and this can, for example, happen if a radical, like the CH3 radical, recombines, reacts with a chlorine radical that is present in the reaction system to form one product molecule, chloromethane. But in this case, we don't have any byproduct. There's no radical at the product site, and this means that the reaction comes to an end here because no radical is there to continue the reaction. Okay, so much about the mechanism of substitution reaction. Thank you guys for watching this video, and I'm looking forward to see you next time. Bye bye!